Okay, in this presentation we are going to look at the negative binomial distribution. So first off, we'll read the question. The annual claim frequency for an insured from a large population of insured individuals is modeled by the following probability distribution. Probability of x equal to x equals this binomial coefficient here. From 1.8 plus x, choose x, times 5 over 6 to the power of alpha, or sorry, to the power of r, or actually it's 2.8 I should say, times 1 over 6 to the power of x. Okay, now the structure is very important. I'm just going to have a glimpse down here at this probability mass function. So just notice here that whatever is to the power of r, I'm stating that as 1 minus p to the power of r. And whatever to the power of the value we're looking for the probability of, that is p to the power of k. Okay, so I argue that that is 1 minus p to the power of r, and that is p to the power of x in this particular notation here where we're looking at x. The binomial coefficient, that is, in this case, as written here, it's k plus r minus 1, and that would make r into 2.8 because k is the variable that we're looking for the probability of. Okay, it's the number of, anyway. So r is going to be 2.8. And that r minus 1 will give us 1.8. Now, just hold that thought for a second, because the hazard of the negative binomial distribution is how these are structured. Okay, so take a lot of time and a lot of care to look at how it's structured and just come up with a statement like that, or a sort of a mapping from values to p and r and x and so on. Okay. The percentage of the population of insured that are expected to have less than 2 claims during a year, and we're asked for the mean and the variance of the number of claims from a randomly selected person. Okay, now this is the probability mass function that we're going to be working with, the probability x equal to k. This is just a formula, so to speak, and I sort of discussed it already. So the binomial coefficient of k plus r minus 1 from k plus 1 minus r, choose k, and that is times 1 minus p to the power of r times p to the power of k. Just something I'll remark upon down here, actually, I just made a mess of it there. Actually, I meant to write it as n from n choose k is equal to from n choose n minus k. Okay, so we could write that as r minus 1 as well. Okay. Anyway, we'll just sort of that can go move back and forward. This gets invoked a lot in the negative binomial distribution. Just watch out for that. Okay, so you could go from this to something else very quickly, and you're expected to be able to follow it. According to this formulation of the probability mass function, the expected value of x is r times p divided by q, and the variance is r times p divided by q squared. Okay, so we've decided that p is 1/6, and 1 minus p, which is q, is 5 over 6. Sorry, q, just in case you're wondering, is 1 minus p, and that is 1 minus 1/6, and that is 5/6. Just to be absolutely crystal clear about that. Okay, so we'll use these two formulas here. Now, the thing about that is that depending on your formulation of the negative binomial distribution, those will change accordingly. So I'm just going to sort of state that this is just sort of lecture notes type stuff, but I just actually sort of state that this is like, let's say you're looking at a book and you see something like this. Okay, you just notice here, watch out for this. This looks just like what I've discussed there, you know, that these two binomial coefficients are interchangeable. So far so good. But what you might not pick up upon here is what we have p to the power of r here. Okay, so this setup inverts what p and r are, p and 1 minus p are. Okay, so that's different from this. So you sort of see we have 1 minus p to the power of r here in my setup, but in another book it might be p to the power of r. Okay, this just actually inverts what is p and q. Okay, what is a success and what is a failure. Just watch out for that. If you're doing it that way, mean and the variance change accordingly. Okay, so I'm not going to call them out there, but just actually the mean and the variance would change as well. Okay, so anyway, that's all the hazard related to this. And that's just a sort of assuming that you're sort of on the same track of what the question is about, because what we're looking at here is when x is the number of failures given our successes, the probability of the mass function of the negative binomial function is as follows. So this counts the number of failures before the first success, or the first r successes. Okay, so you can actually state the negative binomial distribution in terms of the total number of trials given r successes, and you get a different probability mass function there again. Now that we're going at, which actually also has a different mean and a different variance. Okay, so it gets confusing. Okay, and actually that's the point. You have to be very careful and nail it down very quickly, and be very particular about the structure of your probability mass function and how you shape it, because it's much more fluid to the type of things you've probably seen previously. And that's sort of the main hazard with the negative binomial. Anyway, we're going to continue on. So I'm just going to sort of state the question now as is. Okay. Or follow the question. So we're going to use this probability mass function. And what we're asked for is there we go, probability of x equal to, that's a just statement of it there actually. So by inspection we can sort of see that r is 2.8 and p is 1 over 6. Okay. And the probability of x equal to 2 is as follows. 1 plus 8 plus 2. 1.8 plus 2, choose 2. Okay. And that times 5 versus 6 to the power of 2.8, 1 over 6 to the power of 2. Now this is actually important here. So this is sort of like a countdown, so to speak. You could have real numbers here, and essentially it works the same way. You get the hang of it there. So if you were actually trying to calculate 5, something like that, the way you'd sort of you do it after a while is do a sort of countdown. Start at the bottom and just work down to the lowest possible value, and then do the same thing on the numerator. Just have a countdown of the integers, or integers minus 1 each time for the previous one, and just count down till you hit the same target. It's a sort of mental heuristic about how to do these sort of things. It's actually easier than it looks. But anyway, we do the same thing here. So 1.8 plus 2, so that's 3.8. So 3.8 times 2.8, because we can stop there because we hit 1 on the numerator. Okay, same sort of setup. So after that, it's a bit of calculator work. Okay, and we should end up with 0.08844, which is 8.8% essentially. Okay, so that's the sort of second trick there, just getting the hang of those things. They're actually easier than they look. You just do them the exact same way, same approach as you would there, just when you're counting them out. Okay. Hopefully you've had a good bit of practice at this and you know what I'm talking about. Okay. The mean of the number of claims is, according to our setup, is r times p divided by q. That is 2.8 times 1 over 6 divided by 5 over 6, which is 2.8 divided by 5, and that is 0.56. That's straightforward enough. Variance is something similar. R times p divided by q squared, 2.8 by 1 over 6 divided by 5 over 6, and that is 0.672. Okay, that's actually this is actually the expected value of x divided by q, if you want. That's another way of looking at it. Okay, so I just divided by q again. Okay, that's it. So the structure of the negative binomial distribution, very fluid. You have to be very clear about what you're doing, because if you can sort of make loads of mistakes very, very easily if you're not paying attention. All right.